let's start with this online session of the week. This is the fourth week, okay, of the third module of the course. And in this session, we have Muhammad Qureshi. He is a senior scientist. He's specialized on sustainable fuels and circular economy of the VTT Technical Research Center of Finland. He is specialized also in the pyrolysis of waste plastics. He's going to present a short session about 1 hour about this topic. We think it's very interesting. This topic fits very well with the contents of the course. So we think it's going to be very interesting. That's all. Welcome to Muhammad. When you want, you can start.
Thank you very much, Alberto. And for the introduction, maybe I can start my presentation and see if I'm successful in doing that. Normally I'm using Teams, but let's see. Can you see my screen already?
Yeah.
What about now?
Now, yeah, it's okay.
Yeah, full screen.
But on my screen I see also the cameras. So
maybe you can move a bit.
Okay, maybe here. So is this okay? Everything is okay?
Yeah.
The video and the sound.
Mm-hmm.
All right, so I can start my presentation. So this presentation I will be talking about generally about why plastic is relevant, why plastic waste is a problem, what are the recycling techniques that are used, what are the chemical recycling techniques used, and then a bit more deep into plastic pyrolysis, what kind of reactors are used, what is the difference between a catalytic pyrolysis and a thermal pyrolysis, how we can upgrade the products, what is the commercial presence of pyrolysis of plastics, and what are the opportunities and challenges of plastic pyrolysis, and then maybe a very brief outlook into this technology. But the first question that comes to mind when we talk about it, then why is plastic actually relevant at all? Why we are talking about this and why we have this presentation today? Why is it relevant? Well, if you look at the numbers, then you will understand that the plastic industry in Europe is very big. It is close to 1.5 million people are employed in this industry. And approximately 52,000 companies are working in this area, and the turnover in this industry is approximately 33 billion euros. So it's a very big industry, and we all know the importance of plastic, so I don't have to go through that. But also looking at the statistics of plastics production or the demand of plastics, we have seen that it has been rapidly growing since the day it was invented. So it's been skyrocketing, the demand of plastics in different applications, in different products, worldwide production of plastics. And even if you look at the European context, the plastic production is basically increasing and increasing. But I mean, there is a bit of a decrease that we see very recently, and maybe that's one of the reasons of the COVID also, that you see, for example, in the 2019 and 2020, there is a stability. But there is also a lot of let's say research around why plastics can be replaced by some other materials. So we see some change, but overall the demand of plastics production is increasing, and it's going to increase. But if you look closely where this all plastic is going, for instance, in Europe, the demand of plastics by sector, we see that one of the main sectors where plastic is used is basically packaging. approximately half of it, or 40% of the plastics that is in use goes to packaging, followed by construction materials, so buildings and constructions. Then a lot of it goes to automotives, electrical and appliances, and agriculture. So, and you also see on this chart what are the different types of plastics that are used in these sectors, and by the size of it, you can get estimate the use of these plastics in these sectors. But what you see here is that, for instance, polyolefins share the biggest part of the plastics, and they are coming in packaging and also in other areas. But then there are other also polymers that are used in some quantities. But PVC, for instance, is also quite a big polymer that's used in building and construction. And then PET, as in bottles, and in some packaging applications, we see PET is also quite in demand. This gives an idea of what kind of polymers that you will also expect when it comes to recycling, because of course these are the plastics or polymers that will eventually end up as waste. This also gives an estimate of what you can expect. But what happens when it comes to end of life? For instance, this is the statistics from Plastic Europe, the facts from 2021, because they publish it from the previous year. So in 2021, they made statistics about 2020, and from here you can see that approximately 30 million tons of plastic was collected. Plastic waste was collected, and 34% of that was sent to recycling. 42% was sent to energy recovery, and approximately 23% was still sent to landfills. These numbers are, if you look them retrospectively, these numbers are showing good signs, which means that recycling rates have increased in Europe. The energy recovery and landfilling has decreased. So these are giving positive indicators. Also, you see here in this one, in the red square here, is that the export of the plastic outside the Europe has also decreased. These are pointing in the right directions, but are they still enough to meet the requirements or the set targets of the European Union for the recycling of plastics? Maybe not. We have to act faster in order to achieve those targets. I showed you that packaging is one of the main flows of plastics, but if you look at this figure, this shows the global flows of plastic packaging materials in 2013. 78 million tons of plastics was produced, animal production. And if you look at the flow of this, 14% was gone into incineration, 40% was gone into landfilling, 32% was accounted for leakage, and what you call recycling. It's also, you have to understand what is actually recycling. There is closed loop recycling, there is cascaded recycling, and then there's process losses, of course. Closed loop recycling is that when you have polymer, you bring it back to the same polymer or to the same application. So you have a bottle, you make a bottle again, and then you make a bottle again. This is called closed loop recycling. If you take a bottle and you make something which is of inferior quality, that's cascaded recycling. And then in all this recycling process, there is also, of course, losses. So this is very unfortunate, actually, if you see from this, that only 2% of the plastic that was initially in the produce goes into closed loop recycling, and majority of it is not managed properly. So basically, if I sum up this part of the talk, plastic waste management has basically many fronts. If you look at the whole value chain, there are many parts or the pieces of the puzzles that you have to understand. The end of life of plastics. Waste statistics means first you have to understand or quantify where the plastic basically is in, for instance, I mean, in Europe, in which countries have how much of plastics of what quality, how much is their PET, how much is their electronic waste, how much there is construction waste. The statistics is very important. You have to understand that how much of this plastic is available. Then pre-treatment of this waste, because the complexity of this different types of plastic waste is huge. Sometimes you get very nasty compounds in the plastic waste. Sometimes you have different types of impurities in the waste. So the pre-treatment of the plastic waste is quite important part of the value chain. Of course, the recycling technology, what we are talking about today, includes all type of different recycling, mechanical recycling and chemical recycling technologies. What are the products that we are aiming at from this? What are the upgrading techniques to look at? And then, of course, the standardization of this is really important. So when you make a product, you cannot put it in the market unless you have a standard product. So you can make excellent product, but if it is not standardized, then you are not allowed to put it in the market. Legislations are quite important around all plastic waste management, and then the markets. So basically, this whole value chain has many fronts, and at VTT we are aware of all these challenges, and in one or the other projects we are looking into solving these challenges. Then I will go into the recycling techniques. Plastic recycling platforms. This is a bit condensed information here. Plastic waste can be of different types. Municipal waste. Any question here?
No, it's okay.
Okay, I heard something. I cannot see, but I'm just talking.
Yeah.
If there is any question, just please stop me and you can ask.
Okay.
So plastic recycling platforms means what are the different types of plastic recycling platforms are there? If I simplify it, there is municipal waste, there is industrial waste, there is litter from the nature. When it's collected, it can be recycled in mechanically. That means valorization and granulation, and you get back the recycled plastic. Then you have chemical recycling, which can be leached out to polymers, or then different types of depolymerization techniques that can give you monomers. Then there is thermochemical recycling that can include gasification or liquefaction. And then there are also some fancy routes such as this biological and biotech recycling. They are not maybe so well known at the moment and under research, but the topic or the focus of today's presentation is on the pyrolysis part, from which you can get monomers. You can get pyrolysis oil, you can get monomers from there, you can get chemicals, or you can get fuels. If I try to put these technologies in perspective, I don't know, can you see my mouse on the screen?
Yeah.
Indeed, yeah.
Or maybe this is better. So if I start from here, this is the hydrocarbon mixture. So basically from the crude oil, you steam crack it, you get monomers, you make out polymers out of these monomers. So these are plastics. But once you use the plastics, you can basically separately collect it, or you can put it in a mixed waste collection. And from the mixed waste, it goes into a plastic mix, or then it goes directly, if it's good enough, it goes to gasification and back to hydrocarbons. If it is separately collected, then it can go either to sorting and make monostreams, meaning you have very defined streams of polyolefins, or PVC, or different types of PET materials. So if you have monostreams, you can pyrolyze it. You can get back either the hydrocarbon mix, or then you can use a chemical depolymerization technique to get back the monomers. For instance, I will talk about those techniques also in my upcoming slides. But this is to put the technologies in perspective, where these technologies can be used to which type of plastic wastes. If it is very heterogeneous type of waste, you can use gasification or pyrolysis technique. If it is very pure monostream type of material, you can of course use pyrolysis and get the hydrocarbon mixture. Or then if it is clean, then you can also use solvent-based technologies. You can get polymers, or then mechanically recycle it back to polymers, to plastics. This basically explains how different recycling technologies work in an actual value chain. If you look at still a bit more into going into the type of waste, which is because this is important to explain which why we are applying which of the technology, why we are applying mechanical recycling, and why we are applying chemical recycling. So if I say that there's post-industrial type of waste or post-consumer type of waste, it can be scrap, processing scrap that can be monoplastics or mixed plastic, or it can be some other mixed plastics which can come from, for these are the examples of these type of things. For example, if you have a monoplastics, that means you can have a runners or a fallout product. But if you have, for instance, a mixed plastics, it could maybe multi-layered plastics, foils or sheets. So these are all the different examples of different types of waste that is found, and based on these, you can decide where they can be directed. For example, they can be internally used in the process. They can be used internally in the process. These need some sort of recycling or recovery. And for instance, if there is, for example, PET bottle is a good example to say it can be recycled. And then if you look at the quality or the properties of these type of materials, we see that, for instance, this stream is a monostream, which is a bit more clean, and the composition is known. And similarly for others, you can decide based on where the plastic waste is coming from and where it should be directed. Then I will go into the chemical recycling techniques.
We have Muhammad, sorry, there is a question in the chat. Or maybe, do you prefer that we keep them for the end, or?
It's up to you. What do you think is?
Well,
okay
I think
me.
that maybe it's better that we go through, and that we keep all these questions for the end discussion, right?
Okay, that's fine. So it can just you can just type in your questions, and then I can go through them in the end. That's okay?
Yeah, perfect.
Yeah.
Okay. Basically, what makes chemical recycling attractive? There are several reasons why chemical recycling of plastics can be attractive. Well, it can provide you a source of energy, which means pyrolysis oil. It's an eco-friendly fuel in terms of depending on how you think it is produced. It's compared to other types of fuels. It's an eco-friendly fuel comparatively. A range of products means from pyrolysis oil you can actually get to many different chemicals. The food grade material, that means the monomers or the primary building blocks of the plastics that you get from the pyrolysis oil, they are so clean that it can be used into food grade applications. For instance, polystyrene is one polymer that can be depolymerized into styrene, and the styrene you get is very pure, so you can basically make food grade material out of it. Nearly all plastic waste can be recycled, meaning that different types of plastic waste, they are welcome to chemical recycling. If from mechanical recycling perspective, not all plastic waste can be recycled, but from chemical recycling, nearly everything can be recycled one or the other way. You can get chemicals from a waste resource. So you are not putting this into incineration, or to landfill. Instead, you are getting some valuable chemicals. It's environmentally favorable if you compare it with incineration or landfilling, this process. And it's easy integration into existing infrastructure. Means, for instance, pyrolysis or some other chemical recycling technologies, you can just put it in a smaller scale to different industrial units. So it's easily integrated into different places. Then I will go through some types of chemical recycling and give you some examples of it. For instance, solvent-based purification, it's based on the solubility of the polymer in certain type of solvent. So you have a plastic, different types of plastics. For instance, you have multi-layer plastics having two different types of polymers blend together, but you're maybe interested in one of those. So some sort of solvents have solubility for some sort of polymers. So the solvent basically dissolves the polymer and the impurities are removed. And in this type of technique, you get the polymers in very good quality. The downsides of it could be that you need to have a strict upstream sorting system, meaning that the feedstock that you will feed to a solvent-based purification system, you need to have it very consistent quality and not many impurities. So if you are doing a multi-layer plastic of polyamide and polyethylene, then it should be that, because the solvent will only work for that system. So it needs to be pure in that sense. Only homogeneous plastics, that's what it is, are possible. But it has a relatively high technical requirement. The economic and environmental viability is also a bit unclear. There are some examples that I have written here: Creasolve, APK, Polystyrene, Ineos, PureCycle. These companies are using solvent-based purification. They also call it physical recycling, meaning that a polymer chain is not broken in this process. Polymer is just dissolved and then it's retrieved. The polymer chain is not broken. This is why it's called sort of physical recycling. In a chemical recycling, I have put it under chemical recycling because of the reason that I think maybe because of the chemical that I used in this, we can classify also it as chemical recycling. But they claim it as physical recycling because the polymer chain does not get broken in this whole process. Then chemical depolymerization is another method. You have probably studied hydrolysis or alcoholysis or aminolysis lysis. In this one, this is actually exact reverse of polymerization. So in polymerization, monomers join to make polymer, but in this chemical depolymerization, there is a solvent that breaks the polymers into monomers. And very let's say very important example of this type of technique is PET depolymerization. So PET can be depolymerized into its monomers through different techniques. Could be glycolysis, methanolysis, or hydrolysis. It is hydrolysis if water is used as a solvent in this technique. It's alcoholysis if there is alcohol, and it's aminolysis if there is amines that are used as solvent. And this technique is suitable for systems like polymers like PET, polyamide, polyurethanes. In this one also, you need to have strict upstream sorting and only homogeneous plastics. So if you are recycling PET, then you only need to have PET. If you're recycling polyamide, then you need to have polyamides. Mixtures probably are not so welcome in this technique. These are some examples of companies who are using different types of these techniques. Then I come to also thermochemical conversion technique. Thermochemical conversion technique, pyrolysis, which we will talk even more in details in the later slides. It is the thermal degradation of plastics into liquid fuel components, or basically the organic part is vaporized in the thermal, under the thermal basically atmosphere without the use of oxygen. There is no oxygen. It's thermally degraded into smaller molecules. It is suitable to end of life mechanically non-recyclable plastics, well, you can use any type of plastics, but preferably this should be used for those plastics which cannot be recycled mechanically, because mechanical recycling should always be the first option for recycling. But if you cannot do it mechanically, then take it to pyrolysis. In this technique, you recover valuable hydrocarbons, including some monomers that you can repolymerize. Heterogeneous plastics can be treated, so mixtures of plastics. Selectivity and yield can be optimized with a suitable catalyst. So what the product that you want to get and the quantity can be optimized by tuning the parameters of the pyrolysis, or then using some sort of a suitable catalyst. Some mild pre-treatment can be needed in this. It's a bit energy intensive process, but one solution to that is that process gas, which means that when you have condensed all the liquid product, then the gases which are coming out of the process, they are still rich in hydrocarbons, so they can be used as energy for the process itself, which makes the process itself self-sustainable, or you can call it that the gas is providing the energy for the process. The capex of this system can be moderately large, which means that you need higher investment to make this type of system, and post-treatment might be needed depending on the contaminants in the pyrolysis oil. Okay, then I talk about the gasification. Gasification means that you are gasifying everything, gasifying the plastics into syngas, which is carbon monoxide and hydrogen, and they are the building blocks for chemicals. This process is happening at high temperatures in the presence of steam or air, or then carbon monoxide and hydrogen can provide a variety of valuable chemicals through different reaction routes. Pre-treatment is not needed in many cases because gasification is very flexible on the feedstock quality, and heterogeneous waste is possible. But this process is very energy intensive, and gas cleaning, which means the gas that comes out of this process, can be very dirty. So you need to have a gas cleaning step. It requires a lot of investment, high capex, and in order for the gasification to be profitable, large infrastructures are needed. So it cannot be, these systems cannot be made in small scales because they are not really profitable. But then I go into the plastic pyrolysis. If I take the example of polyolefins, you can take these thermochemical pathways. So pyrolysis, gasification, cracking, what kind of products do they give? If you take polyolefins and you thermally pyrolyze it or catalytically pyrolyze it, you have a range of products that you can get: light olefins, aromatics, fuels, or waxes. If you gasify them using, air gasification or steam gasification, you can get energy, or you can gas this carbon monoxide and hydrogen rich gas that can be used for making valuable chemicals, so on and so forth. So these are the different thermochemical recycling pathways for plastics conversion. Then if I look closely into the pyrolysis, what kind of products can we obtain at different reaction conditions? And by that I'm talking mostly about the temperature and the residence time of the reactor. So the temperature, if it is kept at 500, which is a moderate temperature for pyrolysis, and under a thermal pyrolysis, which means no catalyst is used, and if you have very short residence time in the reactor, then the products are basically waxes. Plastics will be converted into waxes. If you have moderately large high temperature, somewhere between 650 and 800 Celsius, with moderate residence time, meaning a bit more residence time than what you can call a short residence time. And by short residence time, I can say that it's between 1 second and 2 seconds. and moderate residence time can be more than that. If you use that at high temperatures, then you get aromatics compound. And then if you have very high temperature, more than 800s, and very short residence time, then you get gases, which are basically rich in light olefins. What are the factors that affects the product distribution? So what are the factors that basically defines what your product would look like from the pyrolysis? Temperature, pressure, heating rate, feed composition, and residence time, and the reactor types, they all are the factors that influence your product in the end. In fast pyrolysis, polyolefins, lower temperatures, you get liquids and waxes at less than 600 Celsius. If you go higher temperatures, you favor the gas formation. Pressure has not so much effect. They are only the effect of pressure is dominant at lower temperatures, but the effect of pressure at high temperatures is not relevant. Heating rate is very relevant. If you have higher heating rate, then you are basically breaking the bonds of the polymer, so you have bond cleavage. But if you're lower heating rate, which means slow pyrolysis, then you basically tend to form char. So there is the secondary product that is char from the plastics. Feedstock composition, which means that what kind of feedstock is welcome for pyrolysis. It as I said, that it welcomes heterogeneous types of plastic waste. It can have polyolefins and other, but preferably PVC and PET should be avoided in the plastic mixture. PVC tends to degrade into chlorine, and PET tends to degrade into acids. So these two polymers should not be in large quantities in the feedstock, because then your oil will be contaminated with halogens, with chlorine, or your oil will be acidic, which is of no value for future use. So these two type of polymers should be avoided. Residence time also has a very important role in pyrolysis. In reactors with longer residence time, you get lighter molecules, weight hydrocarbons, and non-condensable gases. And in short residence time, you get the opposite of that. Reactor types is really very important from the perspective of pyrolysis, and I will go through now, probably in some slides, also deep into what are the different reactor types that are used in pyrolysis. Basically can be categorized into 4 different types of, or mainly, but there are maybe other types, but mainly pyrolysis reactors can be fluidized beds. It can be fluid catalytic cracking system, CSTR reactor, or a screw type of reactor. What is a fixed bed reactor? Basically, they are very small scale reactors in lab scales. They operate in batch mode, which means the plastic is placed in the reactor on a static bed, because it's a fixed bed. So any inert material here could be sand or something, and then you put your plastic here. You heat it up, and then the pyrolysis vapors are condensed in the condensing system, and the gas is collected in a gas bag. It operates in batch mode, so you cannot put the plastic continuously. The heating rate for this system can vary between 5 to 25 centigrades per minute. And the loading of this means how much plastics you put in depends on the type of the system, but it's still very small, 1-200 grams. The continuous inert gas is required for purging the pyrolysis product. So you need to have some sort of driving carrier gas that takes the pyrolysis gas away from the reactor into the condensing system. It can be used as a thermal mode, which is a single stage. You see that only plastic is then degraded and the products are condensed. But on the other hand, it can also be used in 2 stages, which means that the plastic is degraded here and the vapors of this are condensed, are in contact with some sort of a catalyst in a second stage. So catalytic upgrading of the vapors happens here. But these these are lab scale units and good for screening, not really for any production. The advantages and disadvantages of these type of reactors: they are simple construction and easy to build. Economic operations and maintenance of the unit. It can be 1 stage or 2 stage depending on what kind of product you want, and they can be used for in both thermal and catalytic mode. The disadvantage of this type of system is that the temperature controls are difficult because the heating is from the outside and there could be temperature gradients. There is poor heat transfer. Catalyst not replaceable during the operation. So once you have the catalyst, you will just use that. It cannot be replaced during an operation. Bed channeling means that a product can just channel in the bed. It is not distributed, so which can also trigger, some hot spots in the channels, or can lead to secondary reactions forming char or coke. And then this coke deposition on the bed, which means that there is this coke, and then it forms a blockage on the bed, which means that it will increase the pressure drop in the system. Fluidized bed system. In this type of system, you have a bed of inert material, and when you sparge an inert gas through this, then this bed is fluidized. As you can see here in this fluidized mode, that the bed is now is fluidized, and the height of the bed is much larger than what it is initially here, and the packing of the bed material is very different, you can see here. In these type of systems are widely used in plastic pyrolysis, and some of the studies for the research goes back into 1970. And if you want to look up, Kaminsky is one of the person who has done a lot of research in fluidized bed reactors for plastic pyrolysis. They have been tested for up to 30 kilograms per hour on several plastics, and different types of fluidized bed reactors are possible. Circulating fluidized bed, bubbling fluidized bed, or conical spouted bed reactors. Circulating fluidized bed means that the bed basically is entrained into a vessel and is regenerated and then transported back into the reactor. So the bed is moving out of the reactor, goes into the vessel, and then comes back, and it's circulating. This is called circulating fluidized bed. This is very advantageous when you have some sort of a catalyst as a bed material, because in the second step you can regenerate the catalyst and bring it back, so burn away the impurities or the coke from the surface. Bubbling fluidized bed is what you see here. So it's just bubbling, it's not circulating. It stays within the reactor. Conical spouted bed reactors are a special type of fluidized bed reactor with a different geometry, with a cone geometry, which is why it's called conical spouted bed reactors. I will talk more about this in my next slides. Yeah, if I talk about the advantages and disadvantages of this type of reactor. So fluidized bed reactors basically have high heat and mass transfer and solid mixing regimes. They have you can vary the gas residence time in the reactor by adjusting the flow of fluidizing gas. If you have low fluidizing velocity, then you have higher residence time, and if you have higher fluidizing velocity, more gas, then your residence time in the reactor is decreased. So you can vary that by changing the fluidization gas. The product distribution can be flexibly changed depending on what kind of gas resistance time you choose to have. Then it's possible to operate this type of reactor continuously, and it's scalable. It's a suitable alternative to for the use of catalytic cracking in situ, which means that you can have the catalyst in the bed, in the fluidized bed, as in situ cracking. In this one, both thermal and catalytic processes are possible. Maintenance costs are not so high. On the disadvantages side, it has a bit more complex design and operation. Then bed defluidization due to agglomeration under certain poorly optimized working conditions, you can have defluidization. So basically what it means is that if you, for instance, have bigger particles of plastics going into the bed, then they can if the residence time is not enough, they can melt on the surface of for instance, sand or any inert material, and this will defluidize and they will form agglomerates, which means that it's not fluidizing anymore. So the bed will go into the defluidization mode. And if on the other case, if you have the velocity of your fluidization gas not optimized, which means that it's not enough for the bed to fluidize, your bed will be in the defluidization mode. So that's possible, depending on the operational parameters. In this reactor system, a pilot plant is often necessary for a scale up. You need to have a bigger plant to go for the scaled up plant. Attrition of particles can be serious in CFB. So, which means that if you have a circulating fluidized bed, then your particles can break very easily also, because they are continuously moving from one reactor to the regenerator and then coming back and then going forth. So this movement of this bed can cause the particle attrition. They're a bit high, on the higher side of the expense. So the capital cost for making fluidized bed is a bit higher. And in terms of comparison between a bubbling fluidized bed and a circulating fluidized bed, so circulating fluidized bed is also far more expensive than a bubbling fluidized bed. Conical spout bed reactors, they are basically, again, fluidized bed reactor, but have a different geometry. So the reactor is basically a cone-shaped reactor, and this is basically done to maximize the solid mixing regimes. So the mixing in this one, in the fluidizing medium, is quite good. It can handle particles of irregular texture, varying sizes, and fluidized bed. So the proprietors of this technique, they claim that you can have different sizes of material going into the reactor and it will not be a problem. It gives very vigorous gas solid contact. So when there's a fluidization happening, so the gas solid contact is quite good. There's a uniform coating of sand particles with fused plastics. So the plastics that goes inside there, they are quite, the mixing of that is quite good. Short residence time, they will minimize the secondary reactions, which means the formation of coke is minimized. This technique has been used in the pyrolysis of biomass up to 25 kilograms per hour, and operating temperatures can even go up to 500 Celsius. It can be used both in thermal and catalytic cracking. If I look at the advantages and disadvantages of this type of system, there is high heat transfer rate. There is the temperature is uniform. The residence time can be short in this, very short. That's when, and it can be changed depending on the type of the fluidizing velocity you choose. It can be used in continuous operation, and this type of reactor has good control on the operating conditions. You can use it with catalyst, and then I already told you that there is a good contact between solid and gas. On the disadvantages side, the scale up can be of this system can be a bit problematic. The attrition of the bed material can happen, and there can be difficulties for catalyst circulation, and the feeding of the catalyst can be a problem. Catalyst entrainment can be a problem, and by the looks of it, I think the operating cost of this type of system is also a bit on the higher side. Then I go to the fluid catalytic cracking, which is also quite popular in conventional refineries. What happens in this type of reactor is that you have the feed that goes, plastic feed that goes into this riser, and then for instance, the bed material is transported into a regenerator, which can be catalyst, and then it regenerates and it comes back as a regenerated catalyst, and then it's circulated. So it's type of a circulating fluid as bed reactor, which I was just telling you about. And in this type of system, when this is regenerated, it can be used in continuous mode for a long time. Catalyst can be regenerated and comes back. And the gases and the pyrolysis vapor, they leave the system, and it goes to fractionation. Then you can get the products out of it. So basically, it has been used widely in conventional refineries in order to crack the vacuum gas oil into gasoline. There's two zones in this reactor. I just told you, the hot particulate catalyst gets in contact with the feed, and then the catalyst is regenerated. Feedstocks are cracked to gaseous components and further separated to fuels in a fractionation step. But this type of system requires a lot of energy. But on the other hand, it has good solid polymer mixing because of the circulation. Another important type of reactor that's used commercially also is a screw reactor. So this is one example of a screw reactor called Haloclean process from Germany. In this type of reactors, the extruders, basically what you call this, is made up of a tubular reactor. This is a tube that has a conveyor inside, or what you call a screw conveyor. The residence time in this one can be varied by changing the speed of the screw and the length of the reactor. So the time of the plastic degradation depends on how fast the screw is moving, because this will transport the material from this end to this end. And then also depends on the length of this. So if it is of course longer, then you have a longer residence time for the plastics to degrade. In this particular case, the spheres can be used, or they are used in this Haloclean process to avoid any buildup of coke and improve the heat transfer, because they are hot and they are removing any fused plastics on the metal surfaces, and they are just collected here and then recycled back. This system has been used for thermoset materials, for example, printed circuit boards from electronic waste. It has been pyrolyzed in this type of system, and they have used this system for efficient removal of chlorine from mixed waste. There is different heating zones, which means that these heaters on the outside of the reactor can be operated individually. So this can be lower temperature, this can be higher temperature, and this can be higher temperatures, depending on how you want to optimize your reactor. They can be of the same temperature or can be of different temperatures, depending on what you want in the end. Several of these type of reactors are being used also commercially, and they have been used for different types of feedstock, including biomass or tires or something from automotive waste. This have been used. I think I already told you about this part. Then one new emerging technology in pyrolysis is microwave reactors. They are still in a very fancy stage, so which means that they are at very low TRL. There is positive and negative sides of it. They are very attractive for heat transfer, actually. Because of the microwave, it can reach up to 1000 Celsius very easily and very fast, because it's using radiations. But on the other hand, plastics themselves are a poor conductor of electricity, which means that they have to be mixed with some sort of material that improves their conductivity of these radiations. So some sort of carbon is mixed with the plastics in this. It's easy design, but scale up can be difficult, and then mixing of plastics inside microwave reactor can be tricky. But you can combine it with the catalytic upgrading of vapors, and you can get what, depending on what kind of catalyst are you using. Stirred tank reactors are also very interesting and are also quite widely used in this type of systems. They can be internally heated or heated from the outside. They can contain, also catalyst with the plastic inside the reactor, but the upgrading can take outside. So distillation column can be used in together with this type of reactor. So the pyrolysis vapor can go to the catalytic upgrading or fractionation. In this type of reactor, the secondary reactions dominate, means you can get a lot of aromatics, or you can get a lot of char in this type of reactor because of the residence time in the reactor. You have longer residence time, you get secondary products. It can require frequent maintenance, and because of the nature of this product, of this reactor, there can exist also temperature gradients in the reactor. But it has been used in several commercial technologies. Some of them are I have mentioned here in different countries. Just drink some water. But if you look at the bird eye view of these reactors and their properties, for instance, temperature profile, heat exchange, particle size flexibility, flexibility of the residence time, process flexibility itself, thermal pyrolysis, catalytic pyrolysis, what is the value of the products that you obtain from these reactors, what is the scale-up possibility, flexibility of the cost, and then you see that most of the green boxes lie within the fluidized bed systems, but maybe the cost is a bit high. But depending on the other prominent features of the reactors, fluidized beds are very interesting option for reactors for pyrolysis. Then I will jump to catalytic pyrolysis and try to say what is the difference between a catalytic pyrolysis and a thermal pyrolysis. If you look at this picture, there is a comparison of the thermal pyrolysis and catalytic pyrolysis. So in the thermal pyrolysis, there is more energy demand. So basically, if you need to pyrolyze some plastic mixture and it needs 600 Celsius for the degradation in a thermal pyrolysis, it could mean that in a catalytic pyrolysis, it needs 500 because of the use of the catalyst. Catalyst lowers the activation energy or the degradation onset. So there's higher demand of energy in a thermal pyrolysis, which means actually high temperature requirements. And there can be also impurities in the liquid fuel in the thermal pyrolysis if there are impurities in the feedstock. The liquid fuel can contain impurities, can be of low octane number, and then, but on the other hand, it produces high liquid yield with heavy oil. The gases from this pyrolysis, they are produced in less quantities, but can contain carbon monoxide and carbon dioxide. The char from this process contains can be in high quantities, even at low temperatures. But if you use a catalyst for the same process, you have the possibility to remove impurities, because catalyst can also act to absorb some of the impurities. It also means that you would require less energy for the pyrolysis, because you need less temperature for the same degradation. And if you look at the products from the pyrolysis, then the liquid yield is basically decreased, because the gases are increased. You have more cracking, you have more gases, but at the same time, the quality of the liquid is improved, because you have more narrow range of hydrocarbons in the liquid fraction. The gases that are produced from catalytic pyrolysis, they contain a lot of C3 and C4s, valuable compounds. The char can contain well, in the catalytic pyrolysis, the char production is decreased, and especially catalysts having high BT surface area can happen there. If you look at the contrasting picture of the same pyrolysis process for low density polyethylene, on this side you see the thermal degradation product, so the oil of LDPE thermally degraded, and pyrolysis oil of LDPE on the same conditions but with a catalyst. You can immediately see that the range of hydrocarbons in thermal pyrolysis is huge. So you get lots of different compounds in a thermal pyrolysis. But on the other hand, when you use a catalyst, you can actually tune the product, and you get very narrow band of compounds, which is very useful for the next step of purification. And you get what you want. But in this one, you get a lot of different types of unnecessary compounds. This is exactly the same thing, but in a different manner. This picture shows you the cracking of polyethylene with a thermal cracking mode, and then a catalytic cracking mode. With the catalytic cracking mode, you see this sharp and narrow range spectrum of products: gas, gasoline, kerosene. That's it. But on the other hand, if you have a similar pyrolysis done thermally, the range of hydrocarbons is huge. You get lots of waxy and high-end molecules as well. This is why it can be catalytic pyrolysis can be advantageous. What is the effect of the catalyst on the quality of the liquid oil? Basically, the catalyst affects the pyrolysis mechanism and then converts, for instance, if there are heteroatoms like oxygen and nitrogen, into the gaseous phase. It can decrease the halogen content in the oil. So if you have, for instance, chlorine in the oil and you have a suitable catalyst, then by thermal pyrolysis, you can get a lot of chlorine in the oil. But if you have a chlorine in the feedstock and you're using a suitable catalyst, you can capture a lot of chlorine in the catalyst, and then your pyrolysis oil is free of halogens. For instance, a zeolite catalyst can decrease these type of heteroatoms like nitrogen, and it can also decrease phosphorus and sulfur content in the pyrolysis oil. Catalyst can remove oxygenated species from the oil. So for instance, if you have PET in the feedstock, it can induce oxygenated species in the pyrolysis oil. So these type of catalysts can also reduce these oxygenated species from there. The use of the catalyst can increase the quality of the oil by decreasing the viscosity, pour point, density of the oil, and different properties. Basically, here you see what is the effect of of the catalyst on different properties of oil. The density can drop, the viscosity can drop, the octane number can increase, the cetane number can increase, pour point can decrease. So these are the several advantages of using a catalyst that will enable your pyrolysis oil to be useful. You can get some of these properties improved by increasing the temperature, but not all, and to a certain extent only. So what is the effect of the catalyst on the gases produced? Basically, the catalyst, they produce gases, mainly hydrogen, methane, carbon monoxide, carbon dioxide, depending, of course, on the polymer used. For instance, PET can produce a lot of carbon dioxide and carbon monoxide. Polyolefins, they tend to degrade into very olefinic type of gases. For instance, this ZSM5 zeolite can produce gases that contains mainly C3 hydrocarbons from polypropylene and C3 and C4 hydrocarbons from packaging waste. And as I said, light olefins are produced in high quantities with the use of zeolite. So your gas is very valuable. It contains a lot of olefins that can be used to make polyolefins. Then I can quickly jump to other characteristics of the catalyst. Basically, there are various properties of the catalyst that imparts different sorts of characteristics to the process itself. Acidity, surface area, pore size, and the structure of the catalyst. So if acid catalyst basically shows more cracking in pyrolysis compared to a basic catalyst, but at the same time, a high acidic catalyst can produce more gases and decrease the liquid yield, which is not so good. The acid catalyst can also remove impurities from the oil. And the surface, if I talk about the surface area, the simple rule is you have more surface area, you have more cracking. But at the same time, if you have more surface area, you have more cracking, but you have more gases, and then you have decrease in the liquid yield. So there is a compromise where you have to adjust. For instance, zeolites have high surface area, and you can modify the surface area by thermal modification or by milling. Pore size is also very important. On the basis of pore size, I mean, there can be microporous structures or macroporous structures. So microporous structures are small pores and they produce more gases. But if you have macroporous structures, they form liquid primary product and at the outer surface. But if it goes into the pore itself, then you have more cracking inside. So you have lighter compounds. The structure of the catalyst, the crystalline structure, also improves the activity of the catalyst. Zeolites basically have good high internal crystalline structure, but at the same time that also boosts the gas yields and reduce the liquid yields. If I try to show you here in this table, this is basically the pyrolysis of polyethylene over different catalyst, and how does the liquid and the yield and the liquid fraction look like. So if I take a look at the thermal cracking, which is without any catalyst, the liquid yield is 84%, gas is 13%, coke is 3%, and your liquid fraction contains a lot of C6 to C12, but also quite a lot of C13 to C23. So as I showed to you in my previous slide, that the spectrum of the hydrocarbons is quite huge. You get a lot of this, but at the same time, a lot of this as well. But if you use a catalyst, you see that the liquid yield is dropped because of overcracking, which means that from the liquid, you're producing more gases. But at the same time, the liquid fraction contains approximately all of it contains light hydrocarbons in the liquid phase. If you use a white zeolite, which is another type of zeolite, you see that compared to ZSM5, it has a better yield for liquid, and the gases are reduced, but then you can still retain the light hydrocarbons in the liquid fraction. This is the reason why I'm telling you here is all this contrast is that what kind of product is needed in the end will decide what kind of catalyst should be used in the process. Because in the end, these catalyst decides what kind of product spectrum you will have. If you are interested in high olefinic gases, then for instance, ZSM5 will be the choice. If you want to have, let's say, a good share of liquid product in your product spectrum, then maybe you can have a look at this one or this one and still retain quite narrow fraction of hydrocarbons in this range. So it depends on what kind of product you're after. This is well, this was for a pure one polymer HDPE, but this example is from a mixture of polymers. But I will not go into the detail of this one because this shows you exactly what I showed you in my previous slide, that what happens in a thermal and a catalytic pyrolysis with the use of a different catalysts. But maybe one example I can maybe quickly actually show that if you have a thermal pyrolysis of this mixture of polymers, PP, EPS, PET, PVC, pyrolyzed at 450 Celsius, you get 80% liquid and 17% gases. But then if you use ZSM5 in 10%, you decrease the liquid and you increase the gases. So you see, this is again showing you the similar results from the previous slide, that catalyst increases the cracking, but at the same time, it if you look at the composition of the liquid phase, it will be more narrower. System configuration means in what ways you can use the catalyst. You can use it inside the reactor. For instance, in this first example, you have the reactor inside you have the catalyst inside the reactor, which is maybe called in situ catalysis. Or then you can have also catalysts of different types in other vessels. So the product or the pyrolysis vapors leaving from the system can be upgraded in different vessels containing different types of reactors, depending on what kind of product is needed in the end. Or then in a bit more different geometry, you can have a ceramic balls of catalyst inside the reactor rolling like this, and then the gas is taken out from the bottom. I'm just giving you the example of in what ways these can be used, this catalyst. Liquid phase contact. So this is giving you a bit more into how the catalyst can be used. So in this one, good catalyst contact is necessary with the melted plastic waste, for example, in fluidized bed or in fixed bed. Acid catalysts are useful in direct liquid phase, for example, for polyethylene or polypropylene. Large pore size catalysts are needed for good cracking. But these catalysts are also prone to deactivation by impurities such as nitrogen, sulfur, or any other inorganic impurities that can be found in, for instance, municipal waste plastics. Activated carbon is one example which has a very high surface area and is a neutral catalyst and is more resistant to impurities. But in many cases, catalysts can be unrealistic, for example, for municipal waste plastic because it contains a lot of impurities. One way of looking at it is also thermal cracking plus catalytic upgrading, what I told you also in one of the few earlier slides, that you first crack the plastic in a thermal mode, and then you catalytically upgrade the vapors. This can overcome the problem of catalyst getting poisoned by some inorganic impurities, because when you thermally crack it, you can retain maybe solid impurities in a cyclone before you take the pyrolysis vapors into contact with the catalyst. So basically, what you do is low quality hydrocarbons are produced in the first step in the thermal cracking, and then you take this into a secondary reactor which has catalyst, and then you can, with the help of the catalyst, you can obtain high quality fraction. It could be, this is one example of a Fuji process where dechlorination happens at 300 Celsius, because chlorine is volatile at this temperature. You get rid of the chlorine, you thermally crack it in one reactor at 400 Celsius, and then you catalytically upgrade the vapors in a different vessel containing zeolite catalyst. This approach can be continuous or discontinuous, and the liquid product that you get from the thermal cracking can be catalytically hydrocracked also using hydrogen. But acidic sites are also one important factor that influence the product distribution. I already told you how these acidic sites, or let's say the acidity of the catalyst, affects the quality of the oil. In many cases, when you get waxes as a main product, you can catalytically crack also these further into what you want as a liquid. And what, for instance, if you want paraffins or olefins or aromatics, depends on what you want in the end. But what I'm just giving you example here is that if you get waxes as a primary product from pyrolysis of different waste plastics, you can catalytically also crack it further into liquid product. I think I have already told you about the advantages and disadvantages, but very short, very briefly here also. It basically lowers the reaction temperature. It decreases the requirement of the energy decreases. The reaction is much faster. You can have selectivity of the product more towards what you want. So it's not a broad spectrum of compounds. You can actually tune it to the type of the product that you want in the end, and then it can absorb different impurities, for instance, chlorine and etc. On the other hand, the disadvantages of using catalyst, it needs regeneration. So basically, if you're not regenerating, then you are making your catalyst can be deactivated very easily from the impurities. For instance, here acid catalyst can be deactivated by coke deposition. Then it stops being the catalyst. Impurities such as these nitrogens coming out from different plastics, for instance, ABS plastic, acrylonitrile, butadiene, styrene plastic, which is very common in electronic waste. This contains a lot of nitrogen. And for example, sulfur or rubber or tires can contain a lot of sulfur. These type of impurities can deactivate catalyst easily. And for instance, if there is PVC, it can also cause corrosion and form toxic chlorine containing compounds. Very briefly then now about the post-treatment technique. So once you have done the pyrolysis and you have the pyrolysis oil, then you have to look at the quality of the pyrolysis oil. What is needed to improve the properties of the oil. You can do fractionation, you can do blending, hydrotreatment, or dewaxing. Fractionation means that you can take the right products out of your pyrolysis oil by distillation, for example. Blending means that you can blend your pyrolysis oil with some sort of kerosene or diesel oil to improve the properties. Hydrotreatment means you can basically use hydrogen to reduce the concentrations of olefins or saturate the olefins in the product. Dewaxing, I told you about. If there is waxes in the pyrolysis oil or components of the waxes, then you can crack the waxes using some solvent treatment technique or using some sort of a catalytic means for for cracking. I think I have taken a lot of time, so maybe I can selectively go through some additional slides.
I was suggesting, yeah, we are supposed to be ending about 6:30. So it would be good if you could, spare or just to take about 5 minutes more, and then to give some space for discussion or for questions that we have.
Yeah.
So yeah.
Basically, in my other slides, I wanted to give you some examples of different sorts of commercial processes. But I think I can give you the slides and you can look at those examples of these type of plastic pyrolysis commercial systems and what are their characteristics. But maybe very quickly, I have gone through this also already in my speech. The technical opportunities with plastic pyrolysis is that it has a possibility to accept different types of feedstocks. So it has flexibility on the quality of the feedstock. It's a simple process, and the range of product that you can get is you can tune the process to get different types of products. When you have the oil, then it's also a means of storage, energy storage. So you can use it at discrete times. You have the oil, you can use it for energy at different times. The ease of industrial integration means that you can use pyrolysis process in integrating it with some other industry easily. The challenges of the pyrolysis process or thermochemical recycling is that feedstock availability is one. So the feedstock is not as available. Well, it is more available now, but it was not available maybe 10 years ago because lots of feedstock was transported to some developing countries. So it was not available in Europe for recycling. Feedstock selection means that there is a lot of contamination in what feedstock is available. For instance, PVC and PET, they are, I told you that it's not really a required polymer, but they still exist. So feedstock selection is also important. Pre-treatment and material feeding the feedstock to the reactor can be problematic sometimes. So selected pre-treatment is necessary. Choice of reactor is important. Wax formation happens and you have to deal with the waxes in this process. So if you don't have the right condensing system for waxes, then it can be a challenge. Toxicity of feedstock and product means that if you have, for instance, chlorine, bromine in the feedstock coming from different impurities or additives, then it can be nasty. The product can contain hazardous species. The analytical standards means non-existent analytical standard means that the ways to analyze different types of properties of the oil are not standardized. People are using different methods to analyze different properties, so they are not standard methods, which is really necessary if you want to create a standard product. The stability and storage of this is also a bit of a problem because, for instance, the pyrolysis oil is not a thermodynamic product. It tends to change the property of the oil over time. So you cannot maybe even store it because you might form polymerization reaction can happen in the pyrolysis oil. So these type of challenges also are present in the plastic pyrolysis. But with this, I think I can conclude my presentation, and I think the rest of the slides that I have not gone through, maybe can be looked upon later at your pace. Yeah, so I'm ready with this now.
Okay. So thank you. Thank you very much for such a very interesting presentation. I think you have enlightened us with a comprehensive view, I would say, of the state of the art of these different techniques for chemical recycling of plastics, and the advantages and limitations. And I think there have been some questions from our students. I will try not to lose any of them. If I do, please tell me. I think that the first question was from Vesa Taito, who asked about the benefits of having fuel out of the plastic waste versus making energy, producing energy, as both routes end up with CO2 emissions. And I would extend or widen the question a bit, because I think you mentioned that in Europe, in your slides, you mentioned that the fuels obtained from plastic pyrolysis are more environmentally friendly. And I would like to know in what terms you were stating this.
I was saying this in comparison to incineration, for example.
Okay.
Because you have a plastic waste, what are you doing with it? You are either landfilling it or you are either incinerating it. So comparatively, this is an environmentally friendly because you are making use of it. And in terms of circular economy, if you are making products out of it, then it's environmentally friendly.
Okay. So then it's clear. It's not that the fuels are better.
No. Not.
Of course,
it's
if you
in
burn the
comparison.
fuels, you will produce CO2 anyway.
Yeah.
It's true that you are not contaminating the environment with
So it was in comparison with the current recycling, or what you call recycling. But anyways, it's the current techniques.
Yeah. Also a question from Tina Mustonen, who asked why pyrolysis is not yet quite common, and what in your opinion, what would it need to become more used, and in terms of amount of material, or critical amounts of material, how much material should we have, or what would be the requirements of this material? And if you think that, yeah, I was also asking, or going to ask about the legislation, which Tina raised also. If you think that there is a need of changing the legislation, if this would help.
Yeah. So why pyrolysis process is not common? The first question was, right? Actually, pyrolysis process is common, not for plastics, but maybe for biomass it's more common. But plastic itself, recycling of plastic is not very old. It's very recent. I mean, the attention towards plastic recycling is very recent. Maybe only a few years, because as I said, there was no plastic waste in Europe. Everything was going abroad for recycling. But now you have you need to do the recycling, and you are looking at recycling techniques into more detail. And pyrolysis reactors have been in use for quite a long time for biomass, for instance, to convert biomass into bio-oil. But technically speaking, there are technical challenges. I told you, there are various technical challenges and legislative issues that needs to be resolved before this technology can be fully commercialized. There are barriers, for instance, legislative barriers. I would not say that there are big technical barriers, but of course, the technical challenges that I told you are existing. But legislatively, the use of pyrolysis oil is not standardized, which means it's not happening here. There are some demonstration units that are making pyrolysis oil from plastics, but since it's not yet a standardized product, this is why it is not yet in full commercial scale yet. There's research projects going all around over the world, efforts to make this to modify the legislations around it.
Okay. Yeah, things are changing so rapidly, yeah, so quickly that we normally lag behind. Okay, and there was another question from Soile Kalinen. Let's say she asks, yeah, when these systems with these different systems and technologies are tested, if there is an LCA approach, and if the total environmental impacts are calculated at the same time. I would enlarge the question or widen the question, and I would ask from a LCA perspective and environmental impact perspective, from these techniques you have presented, are there differences, or do you think that some of them are more prone to be developed because of their lower environmental impacts?
LCA is not the only way to look at it, but if you compare the LCA of different chemical recycling techniques, then pyrolysis is maybe not the best one, because it needs energy compared to, for example, solvent purification. But in terms of the comparison with incineration, then it's definitely better. So this is one way to look at it.
Sure. Good. So are there more questions between the audience?
This was, I would say 1.5 hours still, but I tried to give you as much information I could, but I think maybe I think I was not successful in giving you all. But I hope that if you have any questions, you can always come back to me and I can try to explain.
Of course, there is a huge amount of information in your presentation. Yeah, it would be nice if you can pass the slides. We will make them available to students in our internal platform for the course. And but well, I think it has been very educative and very enlightening for most of us. And I think we are on time. So if there are no more questions, we in any case we can, if you have further comments or questions you want to address to our speaker today, you can contact us and we can pass them to him. But I think that it's just our duty to acknowledge the fantastic presentation by Muhammad Qureshi today, and thank you for being with us, and hoping that all these technologies get to the market and to our common practices very soon.
They actually, this last slide, I wanted to show you the outlook of this, but maybe I can just quickly share one thing here. And
sure.
This one small thing is this is the where did it go? I don't know if you can see my screen. This is very promising. Investments in chemical recycling. In 2021, plastic producers planned significant investments in chemical recycling technologies, ramping up from 2.6 billion euros in 2025 to 7.2 billion in 2030. So this is a very positive indicator that chemical recycling technologies are now coming into limelight for the better use of it. But if you look at the hierarchy of plastic waste management, it is still down. But you know, if the technology is good, legislations will change.
Great. Okay, so thank you. For the students of the course, well, we are ending now. We will provide you with a questionnaire regarding, well, with some questions regarding today's presentation. We will probably you will have it available from tomorrow, and you will have all the next week answering it. And this is it. So thank you, and hoping to meet you soon.
Thank you very much for the opportunity. It was nice discussing with you.
Great. Okay. Thanks. Bye-bye.
Thanks.
Bye-bye, everybody.
Thank you and bye-bye.
Thank you.
Have a nice
you.
evening.
Bye.
Yes. Thank you.
Thank you. Bye.